Okay, now we're going to check the chemical equilibria side of the Find Someone Who worksheets. I've got them numbered 1 through 16. I'm just going to go through them. Number 1 says, who knows what kinds of substances go into an equilibrium constant expression and what does not? Of course, gases and aqueous solutions go in. Solids and liquids do not. Solids and liquids do not have concentrations of any kind. For number 2, K equals products over reactants raised to their coefficients. You want to be real solid on that. For number 3, someone who knows how to find the standard Gibbs free energy change from an equilibrium constant. That is this equation. With the little 0, that's the standard Gibbs free energy change. K would be the equilibrium constant. You'd have to be given the temperature, make sure it's in Kelvin. And anytime you have R, it's always good to ask yourself which R, which gas constant. This is about energy, Gibbs free energy in this case, but it's still energy. So I'm going to use the R that's in joules, 8.31 joules per mole Kelvin. But then I'd better put this guy in joules, or I know that he'll be in joules when I solve for him. If I want my Gibbs in kilojoules, I will need to move the decimal on the R to move him from joules per mole Kelvin to kilojoules per mole Kelvin. Okay. Number 4 says, who can explain the difference between K and Q? They are both set up just like this, products over reactants raised to their coefficients, but K is at equilibrium and Q is not necessarily at equilibrium. If Q is too big, you have too many products and it will shift left. If Q is too small, you have not enough products and it will shift right. For number 5, how does temperature changes cause shifts in endothermic reactions? If I have an endothermic reaction, heat is like a reactant. Treat it just like any other reactant. So if I increase the temperature on an endothermic system, it would shift right. And if I decrease the temperature on an endothermic system, it will shift left to make more heat, just like any other reactant. Number 6 says, who knows how pressure changes will shift an equilibrium reaction? And we did this in class. If you increase the pressure on an equilibrium system, you are squashing it. It will shift to whichever side has fewer moles of gas. Only the gases count and only their coefficients count. If you decrease the pressure, imagine taking a big breath in, decreasing your pressure, decrease the pressure, and you've expanded, sorry about that bell, and you've expanded your arms way out. You have a huge volume now, and the equilibrium will shift to fill that volume with whichever side has more moles of gas. For number 7, of course, we're referring to this equation. This is in your reference tables. All these equations I'm showing you are on your reference tables. If you have Kp, you can put in R and T and delta N and find Kc and vice versa. But look, it's another R. So let's ask ourselves which R. This is the R because we're relating pressures to molarities. This is the R that would go into the ideal gas law. Okay, 0.0821 liters atmospheres per mole Kelvin. That one, the one that would actually go into the ideal gas law, is the R for this equation. Okay. Number 8 says, who knows how temperature changes affect an exothermic equilibrium? Exothermic heat's coming out, so treat the heat just like any other product. So we're back to this idea, but now heat's on the right. So if I increase the temperature, it will shift left to use up that excess product. And if I decrease the temperature, it will shift right as if to make more of that product. Treat the heat like any other product if it's exothermic. Number 9 says, who knows the sign of delta G when K is greater than Q? So I think of this as Q is less than K, so I don't have enough products. If I don't have enough products, it wants to shift to the right. Oh, shifting to the right means the forward reaction is spontaneous if it wants to shift to the right. If the forward reaction is spontaneous, delta G would be negative. This is the exact reverse situation, number 10. If Q is greater than K, it's like I have too much products. The reverse reaction will happen more. It will shift to the left. If my reverse reaction is going to happen, then my forward reaction is no longer spontaneous at that moment. So delta G would be positive, not spontaneous. When you're talking spontaneous and non-spontaneous, it's always referring to the forward reaction. For number 11, the units depend on whether it's a Kc or Kp, but if it's a Kc, it's got to be molarities, moles per liter. So if you're given moles and liters separately, make sure you divide them so you have molarities. And if it's a Kp for pressure, it's got to be atmospheres. 760 torr, 760 millimeters of mercury, 101.3 kilopascals, all equal 1 atmosphere. So if I have kilopascals, sorry about that bell, if I have kilopascals, I divide by 101.3, and it's atmospheres. If I have torrs, I divide by 760, and then it's atmospheres. Number 12 refers to non-standard Gibbs free energy. We saw this guy earlier. K is at equilibrium. This G is standard. There's another one very near it in your reference tables. If your G is non-standard. Often they'll give you this one, the standard one, or you can figure it out by products minus reactants, multiplying by their coefficients. And Q is just like K, but we're not necessarily at equilibrium. This is all about energy again. So the R has to be the one in joules, 8.31 joules per mole Kelvin, or change it to kilojoules. Whichever units you put on R, you have to match it with your units of G. You either have to change R to match G, which is usually in kilojoules, or you have to change G to match R. He's in joules. Okay. Remember, this for non-standard, this is especially at different pressures. Standard Gibbs is at 1 atmosphere, but a lot of our reactions at equilibrium will happen at higher pressures than 1 atmosphere, and that's why we need our non-standard Gibbs. Okay. 13 says, what happens to K if a reaction is reversed? A little example. If I have an equilibrium where A becomes B, my K expression is, of course, molarity of B over A, products over reactants. If I reverse the reaction, my reactants become products, and my products become reactants. So check it out. Now it's A over B. Look at how these guys are related. They're inverses of each other. So maybe you said that you take the K and raise it to the -1, or you do 1 over your original K, and that's your new K. However you said it, inverses of each other if you reverse the reaction. Okay, what if you double your reaction? Here's a basic reaction. A and B are in equilibrium with C. C is a product, A and B are reactants. So there we go, products over reactants raised to their coefficients. Well, right now all our coefficients are 1. If I double the whole reaction, these are still my products, these are still my reactants, but I'm going to raise them to their coefficients. Look what happens. My original K was this, sorry, C over A, and B, and the whole expression got squared, didn't it? Couldn't you pull the 2 out of each of those? So my original K got squared when my reaction was doubled. You can do that with any relationship. If you triple your reaction, your K will be cubed. If you cut your reaction in half, your K will be square rooted. Whatever happens to the coefficients happens in the exponent of K. Okay, how about intermediate steps, adding up to a larger one? I made this 2-step process here. Here's the K expression for the first step, products over reactants, and here's the K expression for the second step, products over reactants. When I add them up, I find that C is an intermediate. My reactants are really A and B. My products are really D and E for my overall. Well, I'm going to prove to you that if I take the k's of my intermediate steps and multiply them by each other, I get the k overall. Here are the k's of my intermediate steps being multiplied by each other. What cancels out? The c's, the intermediates. I end up with D and E over A and B. DE over AB. Let's see if that makes sense. Yep, DE are products, A and B are reactants for the overall. So the K's of the intermediates multiplied equals the K over all. Okay, and finally, Le Chatelier's principle. An equilibrium will react to reduce a stress. That's one way I've heard it said. A system at equilibrium will shift to reduce a stress. Something about reducing the stress. You've got to minimize the stress. Okay, let's see. Can I spell Le Chatelier? I'm going to close my eyes. L-E-C-H-A-T-E-L-I-E-R apostrophe S. Principle. Okay, study well.